In this video, I want to introduce the notion of using a power series to solve a linear differential equation. Now, a couple of things, maybe three things to notice here. One, I'm going to be talking mainly second order differential equations, but the process works for any order. Two, the example here in this that we'll do in this video will be homogeneous, although the process is very similar for non-homogeneous. In fact, I think in the next video I will do a non-homogeneous example. And thirdly, the book, for whatever reason, switches to x as the independent variable for this section. Well, and the fourth thing is, when we write power series, we write them centered at some x0. And the x0 that we're going to choose is going to be the x0 of the initial condition, right? So we need to know that some functions in here are continuous at that initial condition. So although this is the general way of writing a second order, well, homogeneous equation, the existence and uniqueness theorems apply to this form of it, so that you got to take the capital P of x here and divide everything by it. So if your x0, the independent variable for your initial condition here, if it is at a spot where P is capital P here is equal to 0, then when you divide by it, this lowercase p and q, they will not be continuous at that x0. And all the theorems saying that you're going to have a solution don't apply. So we need to make sure that we have continuity at x0. So x0 is got a special name. It's called an ordinary point, and an ordinary point is one where capital P is not equal to 0. Okay, so that little lowercase p and lowercase q will be continuous at those points. If it's not an ordinary point, then we call it a singular point. We'll see later on this week that when you work with a power series centered at a singular point, that your solutions quite often have strange things going on at that center. We are looking for solutions that are power series, right? And this is how the book generally writes it, as a sum. I have a tendency to write it out like this. I feel like I can see better what's going on and get things lined up right. However, I will do the example in this video written as the book does, and in the next example, which is the next video, I'll write it out more like this. But here we go. I want to start with an example that we actually know the answer to. Here's a differential equation: y double prime plus y equals 0. Another way to say that is second derivative equals minus the function. Sine and cosine are solutions here, right? I know the general solution is c1 cos x plus c2 sine x. I'm going to do this, though, with a power series to show how it works and to see that, yeah, it actually does come up with the solution that we know is correct. So I'm going to do a power series centered at 0. So that would be y equals the sum n equals 0 to infinity of a n x to the n. And one thing to notice here is that, and this is where I kind of like this version of it here, if I plug an x0, in this case 0, if I plug a 0 in for x here, all of these terms are 0 except the first one, right? That is, this first term is a0. But if I plug an x0 in for x and all of this, all those go away and you just get a0. So the a0 in this power series is the y value of generally the initial condition that's given. Likewise, when I take the derivative of this power series, which would look like this, just taking term by term derivatives, when I plug a 0 in now, or if I plugged an x0 into the derivative of this, I get a1. Right? The thing is, the the derivative of this thing here, that would go away. This would just give you an a1, and then this would be 2a2 times x minus x0 to the first power, and so on. So the a1 would be there just as the constant, and that would be what you get by plugging a 0 into the derivative. So the a0 and the a1 turn out to be the function value and the derivative at that initial condition. That's going to be useful later. And here we go. Take the second derivative. Again, just power rule here. Pull the n minus 1 down, drop the exponent by 1. And it's a big sum, so the derivative of the sum is the sum of the derivatives, and they all look the same. They're all power rules with different n's. Right. Now what I want to do is I want to take this. I'll take this second derivative and function and plug it into the differential equation. So here's the second derivative plus the function, and that needs to be equal to 0. So what I need to do now is I need to add this together and see what I can say about the coefficients in front of each of the powers of x. First thing I notice is that this summation here, I don't really need the first two terms, because when you plug in n equals 0 in, that's going to be 0 times all this stuff. And when you plug in n equals 1 in, there's going to be 1 times all this stuff. I mean, when you take the second derivative, the first two terms get killed off, right? So all I'm doing here is saying rather than starting at 0, I'm starting at 2, because the first two terms are 0. Then I notice that this is an x to the n minus 2, or this is an x to the n, and if I want to combine these things, I need a couple of things to happen. I need these to be the same power of x, and I need the indexes to start in the same place. So I'm going to re-index this first one. So rather than an x here, rather than x to the n minus 2, I'm going to do it as an x to the n. And the way I check this out is that I say, well, if the first thing I plugged in is a 2, I'm going to start off with an x to the 0, right? Because 2 minus 2 is 0. So I will change this to an x to the n, but it still needs to start at x to the 0. So this now starts here at n equals 0. Okay. Now, what's happening is everything is going up by 2. This was n minus 2, now it's n. So this n is now n plus 2, and this n minus 1 is n plus 1, and this n is n plus 2. Everything is bumped up by 2, so that this looks like an x to the n when you plug that initial thing in. So luckily here, once I've got that fixed to an x to the n, it turns out that the indexes here are the same. So I can just add these two series now, term by term. So the coefficient here plus the coefficient there times x to the n. Now, because this is a homogeneous equation, I'm saying this power series equals 0 for all x. Essentially, the power series on the left is equal to the power series on the right. But the power series on the right is just all zeros, right? 0 plus 0x plus 0x squared. And so in order for these two to be equal to each other, I have to have that the coefficients here equal the coefficients there. So all of these coefficients have to be equal to 0. And what that gives us is a relationship between one of the coefficients and another one. In this case, a sub n plus 2 is equal to minus a sub n, I'm just solving this equation, divided by n plus 2 over n plus 1. I actually see this better rewriting it this way, rather than saying n plus 2 and n, I'm using n and n minus 2. So here I'm dropping everything down by 2. So the nth term is going to be related to the n minus second term. Okay. Now this is what's called a recurrence relation. That is, if you know one value, then you can use that to find the next value, and then once you know that value, you can use it to find another value, and so on. So here we go. We already noticed that a0 was going to be y1. Since I didn't state an initial condition, this is just going to be left as a variable. Likewise, that a1 is going to be y0 prime. Again, that since it was not stated, this is just a variable at this point. Okay. But now a2, looking right here, a2 is going to be minus a0 over 2 times 1. Right? So I have that. A3 is going to be minus a1 over 3 times 2. A4 is minus a2 over 4 times 3. I'm just plugging in different values of n into this formula. Okay, but at this point here, with A4, saying it's minus A2 over 4 times 3, which it is, but I already know that A2 is this. So I'm replacing the A2 by what it is and then simplifying this fraction. And I get that A4 is A0 divided by 4 factorial, right? Because there's 4 times 3 down there, but there's also a 2 times 1 down there. So it's a 4 factorial. A5 is minus A3 over 5 times 4, but A3 I already know is this, so we plug that in and simplify down to A5 is A1 over 5 factorial. Likewise, A6 is minus A0 over 6 factorial, and A7 is going to be minus A1 over 7 factorial. And I'm noticing a pattern here. If n is even, then A sub n is, and I've got this formula. Certainly it's going to be A0 divided by n factorial, and then there's a plus or minus 1 out in front. So what I'm noticing is that, so it started off with A2 being negative, so the way and then A4 was positive and A6 is negative. Okay, so by doing this, if n is even, I can divide n by 2, and I know it goes in evenly. That'll be an integer. So minus 1 to the n over 2. Notice when n is 2, then this is minus 1 to the 1 power, which is negative. When n is 4, this would be 4 over 2, which is 2. Negative 1 to the 2 power is positive 1. All right? So this alternates back and forth for the evens. And then likewise down here, if n is odd, I'm going to do this n minus 1. Sorry, this minus 1 raised to the n minus 1 over 2 power. Right? If n is 3, for instance, right here, 3, this should be minus a1 over 3. So when n is 3, I've got 3 minus 1 over 2, so that's 2 over 2, which is 1, and minus 1 to the 1 is sure enough minus 1, so I get a minus sign. When it gets up to 5, 5 minus 1 is 4, divided by 2 is 2, minus 1 to the 2 power is 4. Sorry, minus 1 to the 2 power is positive 1, and let's say 1 over n factorial. All right, all of this written out now. The polynomial I have, the power series I have, a0 plus a1x, plus a2, which is this, times x squared, plus a3, which is this, times x cubed, plus a4, x to the 4th, plus a5, x to the 5, and so on. Right. So what I'm going to do with that now is rearrange it. And as I said in previous videos, you're rearranging a power series, changing the order of addition. You got to be very careful. You got to make sure you're within the interval of convergence. So I'm going to state that as I do this rearranging, that I'm only going to consider it valid to be if the x values are within the interval of convergence. So anyway, I'm going to rewrite it so that all of the things with a0 in it come first, and then the stuff with the a1s come afterwards. And then I'm going to factor the a0 out of those and factor the a1 out of these. And what I see is that the stuff times a0 looks just like the Taylor series for cosine, and the stuff times a1 looks just like the Taylor series for sine. And so I get that a0 is cos x plus a1 sine x. Now, if you were doing one of these problems, a student in a introductory differential equations class, I would expect that you could get this far. I would not expect you to then take the step and say, oh, I recognize this as this function, or I recognize that as that function. That takes some time. That takes some getting used to what functions have what power series associated with them. It's not hard. It's just it takes some recognition. It takes some practice. So I would expect you to get this far, and I'd be very happy with that. In fact, sometimes you're not really going to see a pattern very clearly. And so what you can do is you can keep going and get, A6, A7, A8 maybe, and then just say ... I don't see the pattern yet, but I could keep going if I needed to. In which case, you could then split it up into the things with an A0 in front of it and things with an A1 in front of it. And again, without clearly knowing the pattern, at least you could get the first 4 or 5 terms. Let's say 4 terms of each of them. So you might have to get up to a 8. This also is kind of nice in that although I may not be getting the exact answer because I don't have, the full infinite power series here and there, but if I've got 4 or 5 terms on each one of these, then I've got a pretty good approximation of the solution to the differential equation. In fact, you can take a look in the textbook and see some of the pictures that they show. They say, well, here's the first 10 terms and first 11 terms, and you can see that these approximate the solutions rather nicely. In the limit, when you take all of the terms, you get the solution exactly. So there you go. There's a first example of using power series to solve a differential equation.